Hi guys. Today we're going to talk about 12.2, and I skipped 12.1 because it's how to do like linear regression slope hypothesis testing, like to see if we can use our least squares regression line. So we're told this year that's not going to be on the test. However, 12.2, both parts A and B that I'm going to go over, tie in to what we learned in chapter 3. So if this looks really familiar to you, and hopefully it does, it's because it goes with chapter 3 material. All right. So when we looked at that least squares regression model, we saw that it had stuff like y equals a plus b to the x, where a was our y-intercept and b was our slope. If we're dealing with something where it's a power model, and we go back and we look at what power models look like, the most familiar one that you've graphed to date probably is x squared, something that's quadratic. You could also do x to the third power or x to the fourth power, which are like kind of W shaped, depending on if they have all those turns and stuff. But those are our basic power models. So obviously we can't use a least squares regression line to make predictions if our data looks like it has some sort of curve. Now we have to be careful because sometimes these curves, like if you're looking at just the positive values of them, they look maybe like they're not x to the second power, but 2 to the x power. So we're going to split these apart and talk about power models today and then exponential models tomorrow. But the basics of it is if you graph the raw data, like here they have a radius for the x value, I guess I can call that r, on our x-axis. And then on our y-axis, they have volume. If you look at that relationship, it's obviously not linear. So we're going to force it to become linear so that we can go through and then make predictions about what we think X will do or what we think Y will do when we plug in different X's. So here you have your raw data graphed. When the radius is 1, the volume was 4. When the radius was 2, the volume was 34, and so forth. So you have that raw data graphed. And if we look at the residual plot, which we call, E, the difference between our actual and our predicted, that's something from last or chapter 3 as well. Like the residuals are the actual y's minus our predicted y's. We see a pattern in the residuals instead of the scattered stuff that we're supposed to see. So because there's a pattern in the residuals, you definitely can't use a linear model to make predictions. So any power model is something of the format y equals a times x to the p power. So what we're looking at very specifically is if x is the base of your exponent, when x is the base and it's being raised to some sort of power, that's how we define a power model. Okay? So our options to try and fix this then become, we can do 3 different things. If you know what that power is, you can raise your y values to the reciprocal power. But you have to know the relationship in order to do that. So if you remember that relationship between radius and volume, I assume since it's radius, it's either a sphere or a cylinder. If we just look at the volume, if you look at the volume for a sphere, this would be 4/3 pi r cubed. So if you knew that your base, in this case r, was being raised to the third power, you can fix this and we could take the cube root, or v to the 1/3 power, and then our values for x and our units for y would be the same units. You would be comparing inches to inches, not inches to inches cubed. You can also raise your x's to the same power. So if you know that it's a cube, you can raise your x's to the third power, and then x's are cubed at the same time y's are cubed. Oops. R's cubed versus your y's or your volume, which is already cubed. So we have inches cubed and inches cubed. The other thing, which is probably, I guess, the easiest when you don't know what the powers are, is to take either the log or the natural log of both the x's and the y's. And so for us, anyway, that seems to be kind of the easiest thing to do. If I take the natural log of each one, or the log of each one, remember that logs are common logs, they're always base 10. Natural logs are logs with a base e. When you take the log of each side, you're looking at their exponents, and then automatically everything would be lovely and compared to the same thing. So that third option works best when you don't know the power relationship. All right, so if we know the relationship between radius and volume is that, like I said before, if our radius is in inches and volume is in inches cubed, if you know that power, we can raise the volume to the reciprocal power. So if we take our volume and raise it to the 1/3 power, that'd be the same thing as taking the cube root of the volume. Okay, so what that does then is if you take the cube root of the volume, then you also would end up with just inches, right? And now that's where we're comparing the same units to the same units, and that's what's going to make our plot look linear. So here we have our original x. Like there's your original x, which is radius. And then you have your original y's, which are volume. And so in order to fix this, that we don't see something curved, this first option would be to take the cube root of the volume. So that's either going to be volume to the 1/3 power or the cube root of volume. Here's where I would use a calculator and go through and calculate those. The cube root of 4 should be about 1.6. The cube root of 34 is about 3.2. The cube root of 113 is about 4.8. The cube root of 268 would be about 6.447, so 6.4. And the cube root of 524 should be 8.1 about. Okay. So if I take the cube root of each one of these volumes now, and I look at it in my calculator, and I plot a new graph, and I'm looking at still our x values, or our radius would be down here. Okay. So 1, 2, 3, 4, and 5 go across on your x-axis. And now instead of having volume, if I graph the cube root of the volume, let's do 1, 2, 3, 4, 5, 6, 7, 8. There would be 9 up there. And I go through and do a scatter plot of this data, 1 and then 1.6. 2 is about 3.2. 3 outputs 4.8. 4 outputs 6.4. 5 outputs 8.1. We no longer have that same looking curve, right? Much more linear than the data that we had to start with. So that's what we call a transformation to make our power model become linear. Then in our calculator, we can go through and calculate the least squares regression line on this new data. So if you're typing stuff in your calculator, your x's should be in list 1. Okay. If you want to because you're supposed to graph this data first, your y's, your volume, should be in list 2. And then you have your transformed y's, which should be the cube root of your y values, being now in list 3. So if you want to use your calculator to show this scatter plot of list 1 versus list 3, then to find the least squares regression line, you go to Stat, Calc, okay, and then it should be option, on my calculator, it's option number 8, but it should say ln reg a plus bx. It's the second option for linear regression, not the first one. We want to have the y-intercept plus bx. Okay. If you type that all in, it'll give you an a value and a b value, and then you're supposed to build your function. So a for that should be negative 0.013, and b should equal positive 1.6157. Okay. So we have to be careful about how we write this equation. If we defined our variables as x is radius and y is volume, then our least squares regression line would be no longer are we looking at y hat, we have the cube root of volume being predicted with this equation. Okay, when you plug in radius, it predicts the cube root of volume, and then you would have a plus b times x, and in this case, your x is radius. So I kind of squeeze that in there. That's my least squares regression line that I need to use for this next part. So use that prediction equation to find the volume if you're plugging in r is equal to 2.5. So again, you're going to start off with, you're not predicting volume straight off the bat. You're predicting the cube root of volume. 0.13 plus 1.6157, plugging in radius. So when you plug in, our radius is 2.5. Remember to follow order of operations. You're going to multiply first and then add. So 1.6157 times 2.5. Okay. Should be the cube root of volume is being predicted to be 4.02625. Okay. So this would still be inches. Like you plugged in inches, you're getting back out inches, or whatever the units might be. We're not done yet because we didn't want to predict the cube root of volume. We want to predict actual volume. So now to solve this for volume is where you have to remember some algebra 2. To get rid of this cube root, we need to raise it to the third power on both sides. So that gets rid of our cube root. When we raise it to that third power, these would cancel. And you would now be predicting the volume is predicted to be 4.02625 cubed. Raise that to the third power, and you get 65.268. I'm going to round it to 3. So our predicted volume would be inches cubed, right? Or whatever those units might be. So here we plugged in inches, we still have inches, then we cube them, and now you have inches cubed for your volume. And that's kind of the basics of this. Like they want you to be able to realize when you're reading these different axes, like pay attention to what you're plotting, because if the original radius versus volume had some sort of curved pattern to it, you can't use linear regression as it is. So we did a transformation, and this first option, we raised our y to the reciprocal power so that both x's and y's were both inches. So then we had inches versus inches, and that came out to look linear. Okay. And then we were able to run our least squares regression equation model, and then we can use that linear model to make predictions, but then we just have to go back and solve it correctly to find volume. Because when we use that linear model, we solved for the cube root of volume, and so then we had to fix it to make it be volume. We cubed both sides back. Okay. The second option that it talks about is raising the radius to the same power. So in this case, if we're raising it to the same power as the volume, we're going to raise it to the third power. Okay. So volume is in inches cubed, radiuses are in inches. So instead of changing our y values, we're going to change our x's. And if we go through and we cube each one of these, then we have 1, 8, 27, 64, and 125. And then if we go and we graph that data, on our y-axis, we would still have volume. Oops. Writing sideways is hard, guys. Try it. No, I don't. And then on our x-axis, we now have radius cubed. Okay. So pay attention to how they're labeling the axes so that you know what's going on here. All right. I don't want to necessarily scale this correctly or even at all, but you can see I need to go from like 1 all the way up to 125. So if you go like maybe by 50s, that's like super spread out. And if you do kind of the same scale, maybe by hundreds, 100, 200, 300, 400, 500, and you plot these dots, it'd be easier to kind of do it on the calculator. Okay, you should still see something that's fairly linear, not as curved as it was before. It's probably even better looking if I do use technology. So we would do the same thing. We have list 1 or list 2 versus list, I did list 1 versus list 2. And then you can run your least squares regression line that way. So if you compare 1, 8, 27, 64, and 125, and you have then your least squares regression model, it tells me that A would equal 0.007 and B would equal 4.19. Okay. So my least squares regression model for this one, that's using that prediction line, should be y hat equals 0.007 plus 4.19x. Okay. But you have to be careful about what x and y are relating to now. So here, I don't really have x, I have x cubed. All right. So we are predicting volume this time, but what we have to plug into it is the radius cubed. So here they're just giving you radius is 2.5, probably 2.5 inches. If we want to use our equation to model this or to predict it, we're going to need to plug in. So start with that equation. We're going to predict volume. (4.19). We need to plug in radius cubed. So I need to first do order of operations, exponent, then multiplication, then addition. And if you plug that in, (2.5 to the third power would be 15.625. We're going to multiply that by 4.19 and then add 0.007, 007. That gives me a volume of 65.47576 or 575. Okay, so about 65.5 inches cubed. Okay, so remember, both of these were predicting the same thing with the same radius. To see which one is better, you would need to look at S sub E, the standard error and the residuals. You could also compare their R squared values to see how good or how strong those predictions are. Okay, option 3 is the option that I would use if I didn't realize that radius and volume had that cube root relationship. So if you do not know what that pattern is, because you don't have any reference for how those things are related, then your only option is to go through and either take the log or the natural log of both the x's and the y's. Okay, and it doesn't really matter. I'm going to take the natural log of both radius and volume to be able to make them both turn into natural log stuff. They're going to become linear this way. So that's natural log. The natural log of then the radius, the natural log of 0 is just, or sorry, of 1 is just 0. The natural log of 2. The natural log of 3, erase, 1.0986. Natural log of 2. And the natural log of 5. Okay. That would then go on our x-axis. If we then compare that to the natural log of our volume, the natural log of our volume should go on our x-axis. Okay. If you plot that, just trust, you would get something that looks fairly linear. Okay. So if you have this in list 1 and the natural log of the volume in list 2, and you go through and you do your least squares regression line, we should get A is equal to 1.402 and B is equal to 3.025. So for writing our least squares regression line model, we would write this as we're predicting the natural log of volume, and it should go A plus B and then our x, but our x is now the natural log of the radius. Okay. So now we're going to use that same equation. We're going to plug in 2.5 again. So all they're saying is R is 2.5, plug it in. So the natural log of volume is being predicted. When we plug in the natural log of our radius. The only thing we have right now is that the radius is 2.5. So when we plug that in, we're predicting the natural log of volume. So order of operations, we need to start inside the parentheses, and we need to take the natural log of 2.5. Okay, that's a really long decimal, 0.916. I'm going to multiply that by 3.025. Okay, and then I'm going to add 1.402. So I've predicted that the natural log of the volume is 4.173779, blah, blah, blah. I would keep that in my calculator so that I don't have any rounding issues. But then you have to remember, we don't want to have the prediction for the natural log of the volume. We want to solve for volume. So how do we get volume by itself? We have to get rid of a natural log. So to undo a log, we do this thing called exponentiate both sides. To kill off this log, I need to have a base e on both sides of that function. So the base e and the natural log of e, right? It's log base e. They cancel each other out. And then you would just be left with the prediction for volume. Oops, is equal to e to that 4.173 whatever power. And now you can round. And here we're getting about 65 inches cubed for that final answer. So they all should be about the same. Like here I got 65 perfectly. There I got 65.5. Here I got 65.3. And I didn't write them down, but each time we did that least squares regression line, it should have told you R and R squared. The one that's the strongest R squared value, or even R value, whichever one has the strongest correlation between X and Y would be the one that I would want to choose. Okay. But for ease of simplicity, that option 3 is usually the one that we would pick because we don't know maybe the relationship between our X's and our Y's. So again, what is a power model? Okay. It's any function where the relationship where X is the base and it's being raised to some sort of power. So we talked about like there's different kinds. And what's difficult here is that, like for the most part, whenever we go to graph our data, most of our data is only going to show us positive values of X. So if you're not looking for it or you see this curve in your data, you may not recognize that it's a power model. Okay. The ways to fix it are threefold. Our first option is make, our Y's to the reciprocal power so that they match those X's. Your second option is to raise your X's to the same powers as the Y's. Okay. So this is like changing list 2. This is changing list 1. And so that when you go to do your linear regression, here I would want to do list 1, which are your original X's, versus your list 3, which is your new Y's. Okay. Here, I'm changing list 1. So my linear regression would be like that list 3, which is your x's raised to the same power as your y's versus your y's. Our last option is to take the natural log of x's and the natural log of y's, or the log base 10 of x and the log base 10 of y, so that now like your linear regression would technically be like new list 3 and 4, where you have the natural log of x and the natural log of y. Okay, so those are our options. So this is changing both. All right. Please let me know if you have some questions, and we'll talk about exponential models tomorrow.